Okay, we still have a small amount of material to cover for Chapter 5. This is actually Section 5.4 in your book. Section 5.4 deals with calorimetry. The lab that you guys will be doing, either this week or next week, will be a calorimetry lab, so I hope that it will reiterate what we're talking about. In calorimetry, it's when we measure heat changes. And now remember, heat is Q. So in calorimetry, we're measuring heat changes, and a good way to measure heat changes would be by monitoring the temperature. But again, realize they're not the same. There's a formula for calorimetry, and that formula is Q equals ms delta T, where Q is heat. And we know that the units of heat are usually joules. Sometimes if we're dealing with large amounts of heat, we'll report those units in kilojoules. M as you would see it in other formulas. M is mass, okay? The symbol for M is mass. If you put M after a number, it means meter. But in a formula like this, it means mass. Mass in this equation needs to be in grams. S is specific heat, and I'm going to talk more about that in just a moment on the next slide. And what is triangle T? Triangle means change in, T is temperature. So this is the change in temperature. And y'all know that to measure a change, you have to subtract numbers. But remember, the order you subtract them is important. How do you measure a change in something? It's the final temperature minus the initial temperature. And most often when using this equation, that's going to be degrees Celsius for the units, okay? So these are your most often units that you would use when you're doing calorimetry. Let me tell you how you actually know your units by talking more to you about the specific heat. The specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Okay? So it's how much heat it takes for something to experience a temperature change. When something burns you, it's the heat that burns you. It's the Q that burns you. Have you guys ever heard that a burn from steam, from water vapor, is worse than a burn from hot water? Okay? If you haven't, you're hearing it now, but a steam burn is bad. Have you ever been straining noodles in the sink after you cooked them and that steam in the colander, that steam came up and maybe got on your hand or whatever? And you might have not realized it, but that is the reason it hurts worse is because steam has got a whole lot more Q in it. It's got more heat than boiling water. So there's a lot of heat, there's a lot of energy there. Another reason that a steam burn hurts more is because y'all know that to go from liquid water to steam, the water molecules spread out a little bit. And so there's more surface area to the steam. So it can do more damage because it can cover more area. Again, another thing about specific heat. When you get your clothes out of the dryer, sometimes they feel good because they're warm, right? But y'all, when you get your clothes out of the dryer, how does the zipper feel or the metal button on your pants? It doesn't always feel good, right? So the clothes, why? Because it feels hotter. The clothes in the dryer, they've all been exposed to the same amount of heat. But the towels and the cotton part of your jeans, those just feel good and warm. They've absorbed the heat and they haven't experienced a big change in temperature. Okay, but the buttons are made of metal. Metals have low specific heat. And the symbol for specific heat, of course, is S. So metals have a low specific heat, very small numbers. That means it doesn't take a lot of heat, a lot of Q, for the temperature of the metal to go up. Okay, so they can hold on to a lot of heat and their temperature goes up. There is an interesting story in your book about specific heat, and y'all, I just think it's something neat to talk about. It's on page 205 in your book. So you guys should read about that. It's about hypothermia, and it talks about water's specific heat. And y'all, the specific heat of water, the S for water, is 4.184 joules per gram times degrees Celsius. Specific heats are known. Like for water, it's always that, 4.184 joules per gram times degrees Celsius. So if you know the substance is aluminum, then you can look up the specific heat. There's a table in your book. It's table 5.2. It's on page 200 that lists some specific heats. You don't have to memorize those, but if you're given a problem and it talks to you about calculating the specific heat of, or the heat of copper or the mass of copper, and you're using this calorimetry formula, if you know it's copper, you can go to this table and look up the specific heat of it to plug in that formula. But anyway, going back to this story in your book that's on page 205, y'all, your body is about 70% water. Okay, and water has a very high specific heat. That means that fluctuations in our body temperature are small because water can absorb a whole lot of heat and your body doesn't experience a temperature change. So y'all know that, a normal body temperature is 98.6 Fahrenheit. And anything above that is a fever. And a fever of 103 or 104, that's a high fever. It's more dangerous in an adult than it is in a child. But that's a really high fever. Anything above that it's extremely harmful. Okay, so that's not a big fluctuation from where the body temperature normally is. And y'all also have probably heard about, like in August, when spring training starts for football. And y'all know when you're exercising, especially when you're outside like that, it's important to stay hydrated. And every year we hear about spring training at football practice. An athlete got dehydrated and their body overheated. Well, dehydrated means they didn't have enough water. And water is important in our body to help maintain our body temperature. But the story in your book is about a woman by the name of Anna Bagenholm. And I don't think the book records a year, but you could read it and you can Google more about it. Anna was snow skiing, and she ended up off the regular path for skiing, and she got trapped under the ice. She broke through ice and was trapped under the ice in water. And naturally, when your body goes into freezing cold water like that, your body starts to lose heat. Okay, so she was losing heat. The way the story goes, and I don't know if this part's in your book, but I had Googled it at one point and read more about it. She was able to find a little air pocket under the ice and breathe for a little bit, but y'all, she was stuck. She couldn't get out. And her friends came to her and found her, and they could not pull her out. And she was trapped, I want to say it was close to an hour. It says in the book that she spent over an hour trapped under the ice. And so when they got her out, they could not measure a heart rate. And it's because her body temperature had dropped so low. And she actually holds, I believe, the world record for the lowest body temperature ever recorded on a human being who survived. Her body temperature was 13.7 degrees Celsius, and I think that's around, I can't remember if it's like 60 degrees Fahrenheit, I think is what it is. I'll have to double check that. But that's just some information about specific heat.